Hey everyone, this series of videos is going to take you through lesson 9I, which is essentially the culminating lesson of this chapter, and it's applications of logs, which means, in a nutshell, that we're going to look at the types of problems for which logs actually help in reality with situational problems, situations that could, in theory, mimic real life scenarios, and the types of problems that you'll inevitably see in math analysis or in calculus if you start to get further and further in the mathematics world. Now, the important thing to understand about this playlist of videos is that it's basically like a video answer key. There's nothing new to learn on pages 16 and 17 because these problems are simply applications of skills we've already talked about. So in theory, you don't need to watch any of these videos to be able to do these questions. I'm going to do all of the assigned questions, one video per problem, so that you have something that you can work through while you're looking at the answer key on your own. But you don't need to watch these videos, especially if you already kind of understand how logs work and feel confident that you can do these problems with the answer key alone. The videos are just meant to give you a little bit more of the detail that goes into where I got my answers from. So you decide. You can watch any of these videos, you can watch some of these videos, or you can watch like one and then be done. So you decide, but the purpose of this lesson is meant to be an application. So you're not going to learn anything new, you're just going to see what you've learned in a different light. In question number 1, for example, we're going to deal with something that is by nature an application of a log type problem. Application usually means real life scenario, or a question that doesn't necessarily look like a log problem that we have to translate into a log problem. So let's take a look a little bit more deeply at the question so we can see where the log is sort of hiding here. It's got this lady who wants to freeze a freshly baked loaf of bread. At the time she put it in the freezer, the bread had an internal temperature of 105 degrees. Usually numbers are important, so I'll circle that. The bread's internal temperature will decrease 15% each hour it's in the freezer. So I'll circle that information as well. First, because it's a number, and secondly, because the word decrease reminds me of those exponential type problems we did in the previous chapter. And the word decrease with the 15% next to it tips me off that this is probably going to be one of those percent multiplier questions. Percent multipliers came up a lot when we were dealing with exponential problems. So if you need to go back to the chapter 8 packet and look up the lesson on percent multipliers, it might be a good idea to do so, because that's where we're going to really base our thinking for question letter A. To write an equation that represents the temperature of the bread, we'll need to understand how this relationship translates. The first thing that you'll want to remember is that anything that involves a percent multiplier is by nature a geometric or an exponential situation. That means its equation has to fit the geometric or exponential structure, namely that it will have an initial value times a multiplier to the power of the variable, x, n, t, whatever you're going to use. Now, through that lens, we'll reread the question and try to look for this important information. When she put it in the freezer, the bread had an internal temperature of 105 degrees. I think the implication there is 105 must have been the initial temperature, because that was when she started. That was what was happening when she initially put the bread into the freezer. So 105 seems to be a logical interpretation for the initial value. Now the multiplier is going to come from this decrease of 15%, and hopefully this reminds you again of those percent multiplier questions we did, where we took 100% of the temperature that we started with, minus, because we're decreasing, 15% per hour. So that tells us what percentage we're dealing with. We're dealing with 85% of the temp every hour. 85% is not the multiplier, but if we move the decimal point 2 places to the left, that does give us a multiplier of 0.85. Again, you can go back to the previous lesson and revise your thinking if for some reason you forgot where that information comes from. But we know now that 0.85 must be the multiplier. If I think about the context of this question, then I can put together that 105 times 0.85 to the power of x must be the equation that represents the temperature of the bread every hour. So x in this context represents how many hours the bread has been in the freezer. So I'll write my equation, y equals 105 times 0.85 to the power of x. And I'll remind myself that x is hours. Some people use t for time instead of x. That's fine. You can do whatever you want with the variable. Now in letter B, it says to use guess and check to determine how long it'll take for the bread's internal temperature to be less than 5 degrees. So guess and check immediately makes me think, oh gosh, if I need to do this by guess and check, that means I'm going to need a calculator, so definitely make sure you have one of those, and I'm going to need time and patience, which you might not be able to just pull quickly onto the screen. So one thing that you could do, in theory, is to think about using technology to guide you. If you happen to have a graphing calculator that has a y equals button, this is one way that you can kind of quickly narrow down the answer without guessing and checking a million possibilities. You could type 105 times 0.85 to the power of x into the y equals menu. You can go to the table of values and you can scroll in the table, because remember x is the number of hours. Y must be the temperature of the bread. Remember initially the temperature was 105, there it is. After 1 hour the temp dropped to 89. After 2 hours the temp drops to 75. Well, if I keep scrolling until I get close to 5 degrees, it looks like 5 degrees is going to happen somewhere between 18 and 19. Because at 18 I'm at 5.6 degrees. At 19, I'm at 4.7 degrees, so clearly it had to happen somewhere between 18 and 19 hours. And now if I have to guess and check, at least that gives me a fairly small window of numbers to try. So I could do, for example, 105 times 0.85 to the power of, let's split the difference, 18.5. And I would say, ooh, that's pretty close. It's definitely not bad, but it looks like I need to maybe make a slightly bigger power, because at this time I'm only at 5.2-ish, and I need to go all the way down to 5. So we could use the copy and paste feature of our calculator. We could try a bigger decimal, 5.02. It looks like I'm getting closer, so I'll keep making the decimal bigger. Down to 4.9. So clearly it had to happen between 18.7 and 18.8. So maybe 18.75, and we can keep revising our answer a little bit more. Looks like I've gotten pretty close. 18.73. That's not bad. 18.73 hours must be the approximate time it will take in order for the bread's temp to be less than 5 degrees. Now, this is where you'd say to yourself, okay, Herbert, but what do I do if I don't have a graphing calculator? What if I just want to solve this with a normal calculator or no fancy calculator at all? Like, what could I do? In letter C, you could have totally solved this equation with logs. Now, going back for a second, remind yourself, the part that we knew was the y value. Y was the temp of the bread. X was the number of hours. We didn't know initially that it was going to take 18.73 hours, but we knew that the temp had to be 5 degrees. So if I plug 5 into the equation for the letter y, and then solved the equation, 105 times 0.85 to the power of x equals 5, I could actually get an answer directly. Here's how. First, let's focus on getting x by itself. Remember how the general wisdom of algebra is to work from the outside in, get rid of anything that's subtracting or adding first, then get rid of anything that's multiplying or dividing, then work on parentheses and exponents. Well, I've got something that is multiplying. I'll get rid of that. I'll divide both sides by 105. That'll cancel that out. Now 5 divided by 105 is not going to be a nice number, but that's okay. 5 divided by 105, whoops, you can't see that, is 0.0476. Not nice, but 0.0476. equals 0.85 to the power of x. Does that type of problem look familiar? Hope so. That looks like one of the log questions that we were doing a couple lessons ago. That looks like what we were doing on, and if you want to flip back in your packet just for reference sake, page 10. Remember those problems with the power property? Where it looked like something, oops, so you can see it, looked like something exponential equal to a number? Well, the numbers aren't quite as nice here, but we definitely have something exponential equal to a number. And if you saved your steps from those problems, you might remember what to do. Introduce a log into this problem. Write a log on both sides of this question. So, and I'll use scratch paper so I don't run out of space here, log of 0.0476 equals log of 0.85 to the x. Remember why we write log? It's so we can bring that x, currently a power, not very helpful as it's hanging up there like that, bring that x down to the front of the question as an exponent. So I have log 0.0476 remaining unchanged equals x times log 0.85, which again seems unremarkable till we realize, hey, this makes a problem that we can do. X times, well, I can get rid of something times, I'll just divide it to the other side. And if I divide it to the other side over here, that means log of 0.85 cancels out. X is by itself on the right hand side, that's what we want. And we have these messy, horrible looking decimals, but even a standard calculator with a log button, even a phone calculator can do this. Log of, I'll just have to be patient, 0.0476, close parentheses, divided by log of 0.85 gives us, drum roll, 18.73. Now technically it was 18.74 if you rounded it to decimal places, and I'll admit I kind of quit on my guessing and checking before I had a chance to be more precise, but the point stands. You can solve this without guess and check. If right now you're looking at this process going, Herbert, I'd rather just guess and check. Like, look at all this work. That was so messy. That's completely fine. If you'd rather solve by guess and check, it's totally okay to do that. Just recognize you have options now. If you understand logs, that gives you an option to solve this problem. If you understand guess and check, that gives you an option. If you have a graphing calculator with the table capability and a little bit of patience to guess and check, that gives you an option. The point is that you have options. So decide which way works best for you and try to do every question in pages 16 and 17 with your choice, whatever that may be, so that you can pick a lane and just get really, really good at deciding how you're going to do the problems and using that method consistently over and over and over again.